Dear students, my name is Keponga Wantoku Chacha. I'm going to give a lecture on the linear algebra 1, which is OMT 112. And here I'm going on to talk on knowledge area 1, which is going to cover the following things: real number field axioms, demonstration of vectors in 2 dimensions and 3 dimensions, norm and distance, and operation on vectors. We are going to see all these 5 operations on vectors. So let's start with the first part, real number field axioms. What is a real number? A real number is the value of continuous quantity that can be represented on a number line. Or you can say is a set of continuous quantity. And this can be denoted by R. I think you can see it there. By R. That can be written in that way. So, what do you mean when you say axioms? Axioms are the properties. And here, we are going to see the properties or the algebraic properties on the real numbers. And this is called the real number field because of these axioms. Satisfies about 9 axioms. So the first axiom here is commutative property of addition. Let's say we have 2 real numbers, A and B. If you take A plus B, and then this is equal to B plus A. If it's obeyed, that property called commutative property. The second one is associative property or associativity property of addition. And the third one is addition identity property, whereby 0 is an additive identity property. So it means every real number plus 0, you get that number. And also we have additive inverse property. For example, if you have A, the negative of A is additive inverse of A. And then you have the first 4 axioms are for addition. The next thing are for multiplication. And then you have, we have the same property that the commutative property of multiplication. It means if we take 2 real numbers, let's say A and B, we take A times B, this is equal to B times A for all real numbers. So, next thing, we have also associativity property of multiplication. That obeys this property. If we take A times, in bracket, B times C, this is equal to, if you take A times B in bracket, then you multiply by C. For all real numbers, this is satisfied. Also, we have multiplicative identity property. The number that if you multiply to every real number, you get that real number. The number is 1. 1 is multiplicative identity. So if you take 1 times every real number, you get that real number. Property number 8 is called the multiplicative inverse property. The number that if you multiply to another number, you get the multiplicative identity, which is 1. So for example, if you have A, you multiply with the inverse of A, multiplicative inverse of A, you get 1. For example, if you have A, multiplicative inverse of A is 1 over A. For example, you have 2, the multiplicative inverse of 2 is 1 over 2. Lastly, we have distributive property. Distributive property is the property that obeys this property. That if you have 1 real number, let's call it A, and then you add 2 real numbers, let's call them B and C, as I have shown here, then This is equal to A times B, and then A plus A times C for all real numbers. Okay, next part. The next part, you are going to see the demonstration of vectors in 2 and 3 dimensions. Okay, dear students, let's know what's a vector. A vector is any quantity that have magnitude and direction. So, we are going to see this kind of quantities in 2 and 3 dimensions. Okay, let's first see a vector in 2 dimensions. A vector in 2 dimensions of real space are vectors which are presented in 2-dimensional plane. For example, the vector in 2-dimensional space are just described by a pair of only 2 entries. Let's say x and y. For example, as it has shown here. So, how can you get a vector? Or what makes a vector to be a vector? A vector should have an initial point and terminal point. And if you take the subtraction of the terminal point minus initial point, you get a vector which has the magnitude and the direction. So, for example, this is has shown here geometrically. This is a vector starting from the initial point A to the terminal point B. So, and this line from A to B shows the magnitude of the vector, and the arrow shows the direction. And the direction mathematically can be shown by either an angle, or can be shown by the normal direction, east or west or north or west, and so on. So let's go to the furthermore. Suppose we have a vector v. This is the way how vector can be represented with right-hand arrow. So this vector has started from initial point, which is 0, and ending at the terminal point, which has 2 entries, v1 and v2. So this figure illustrates the vector in 2 dimensions. So let's see the vectors in 3 dimensions. The same as you have seen the vectors in 2 dimensions, that it is a pair of 2 entries. Here we have triple entries. Also, it must have an initial point and the terminal point. But every point should have the 3 entries. For example, here we have a vector starting from the origin 0, 0, 0, and its terminal point is v1, v2, v3. And now the vector v is equal to just v1. It has 2 entries, v1, v2, and v3. That means if you subtract the terminal point to the initial point, we remain with v1, v2, and v3. Okay, this is an example how we can find a vector if you have given the 2 points, the initial point and the terminal point. Example, find a vector AB that starts at A equal to 4, -2, 9, and ends at a terminal point B, which is equal to -7, 0, 6. This is our solution, and this is how we can represent a vector that's starting from A to B. We write AB and an arrow above, and to find that vector, we take the terminal point B minus the initial point A. Okay, so here, just taking the terminal point, which is this one, -7, 0, 6, minus the initial point, which are the entries 4, -2, 9. And then, by doing the normal subtraction, we get -11, 2, 3. And this is our vector AB. Next thing. The next part is norm and distance. In the vectors, we start norm and distance. And this is our slightly difference. So let's start looking what's norm. Norm is just the magnitude of the vector. And this is denoted by norm V. We put vector and put some norm or the absolute signs. Furthermore, how can we find this norm? It's just a square root of the sum of the squares of the entries of the vector, like it has shown here. And this is for a vector of n dimension, means with n entries. So, what about the vector with only 2 entries? It's just the square root of the sum of the squares of the entries of that vector. We know the vector in 2 dimensions has 2 entries. So, and these, let's call them V1 and V2. Just the square root of the sum of square V1 plus the square of V2. Likewise, for vectors in 3 dimensions, we take the square root of the sum of the vector, which this vector in 3 dimensions has 3 entries. So that's why we have the square root of V1 square plus V2 square plus V3 square. So this is what we call norm. And remember, we are looking just vectors in 2 and 3 dimensions. So don't need to discuss about the n dimension. So this is an example. Example 1, compute the norms of the given vectors. We have given vector B in A, which has 3 entries. It means this is in 3 dimensions. And we have another question, part B, also it is vector B with 2 entries. So we ask you to find the norm of this vector. So from the formula, as you have seen from the definition of the norm, it's just the square of the sum, the square root of the sum of the squares of the entries of the vector. So, dear students, we are just going to substitute the entries. The first entries at V1, the second entries at V2, and the third entries at V3. So, for A, we just take the square root of -5 square plus 3 square plus 9 square, as it has shown here. So after finding the square, we get this result here. And then the square of this one will give you the sum of this result 25, 9, and 81 gives you 115. So now the norm of the vectors given at A, it is the square root of 115. And also the same to question B, which is finding the norm of the vector. Here we have just 2 entries. Just to take the square root of the squares, the sum of the squares of the 2 entries. which are 3 and 9. Now we get the square root of 9. So let's go next. Here we're going to see what is the distance between vectors. So how can we find the distance between vectors? Dear student, we just find the norm of the difference between the vectors. Suppose we have given vector u and vector v, and these are the n-dimension vectors. Just generalizing. So this is the formula. We take the norm of u minus v, vector u minus vector v, and then equal to the under root or the square root of the difference between the corresponding entries of the two vectors given. So for example here, we have given two vectors, u and v. We are asking to compute d of vector u and vector v. That means the distance between u and v. So let's go to see the calculation. Dear students, let's see the example on how to compute the distance between vectors. Here we are given vector u and vector v, and you're asking to find the distance. So, solution. The distance is just taking the norm of the difference of these two vectors. And here we have two vectors which are in 3 dimensions. So each vector has 3 entries. So we take the square root. Let's say this is u1, the first entry u1, u2, u3, and this is v1, v2, v3. So the distance defines the difference between this one. Taking u1 minus v1, the corresponding component of the other vector, square, plus u2 minus v2, square, plus u3 minus v3, square. So dear students, remember u1 equal to 1 minus v1 is 0, you put square, plus u2 equals 2 minus v2 is negative 3. So this will be plus the third entry in vector u is 3 minus the third entry in vector v is 2, then square. So 1 minus 0 is 1, square is 1, 2 plus 3 is 5, square is 25, and then 3 minus 2 is 1, the square of 1 is 1. So 1 plus 25 plus 1 gives the under root of 27. So therefore, the distance between these two vectors, u and v, equals 27 units of distance. Okay, let's continue. Let's go to the next part. Okay, the next part is about the operation on vectors. The first operation we are going to see here is addition. Addition of vector. So let's consider, let's say we have two vectors, u and v. To add these two vectors, we get another vector. It's just by taking the addition of the corresponding components of the vector. So the vector u has two entries, u1 and U2. And vector V has two entries, V1 and V2. So taking U1 vector U plus vector V is just taking U1 plus V1, comma, U2 plus V2 in pair. So let's see an example. Just to remind you, another thing that addition of vectors result to the resultant of vectors. For example, we have two vectors here, U and V. This vector and this vector. So we are asking you to find the sum of these two vectors. So to add these two vectors, as I have told you from the definition of adding two vectors, is just adding the corresponding components of the vectors. So this vector, these two vectors are in 3 dimensions. So it's just taking, for example, here you take 1 plus 3, the corresponding first components of the vector, and the 2 plus 2, the corresponding second components of the vectors, and then 3 plus 1, the third corresponding components of the vectors. Now it results here, and then you get 4, 4, 4, the entries of the resultant. Okay, that's about addition. Let's demonstrate this addition. We have two vectors. Let's say this vector is called V, and another vector is vector W. So add these two vectors. Here we have vector V and W. Then adding them will get a resultant from the initial point of the first vector to the terminal point of the second vector. So that's about addition of vectors. So let's go to subtraction of vectors. Subtraction of vectors works the same like addition of vectors. When you subtract two vectors, also we get a resultant or the two vectors. So let's say we have vector U and vector V. We want to add these two vectors. It's just subtracting the corresponding vector, corresponding components of the two vectors. For example, these two vectors all are in 3 dimensions. It's just subtracting the first corresponding components of the vectors, the second corresponding component of the vectors, and the third corresponding component of the vectors. Simply like this, and then we get the vector or the resultant, which has 3 entries, 2, 0, and 2. Okay, this is how it looks geometrically. If you have, let's say this vector U and this vector V. If you subtract these two vectors, it means you are taking V, take away vector U. It's like taking vector V plus the negative vector U, which is this one. And this vector is the same as this vector. So this one, the negative of this one, this vector is the same as this one. So this, the resultant, will get us subtracting two vectors. Okay, let's go to the next step, called the scalar multiplication of vectors. The scalar multiplication of vectors is multiplying a vector with a scalar. Multiplying a vector with a scalar. A scalar is any real number, and the vector, its definition remains the same. So how can we multiply this one? Let's say, suppose we have a vector V, and we have another scalar, call it alpha. If you want to multiply alpha and a vector V, you just take the char alpha multiplying to every component of the vector or every entry of the vector. For example, you have to find alpha v. This is equal to alpha times every entry of vector v. For example, here we are given an example. Vector v, which has entries 1, 2, and 3. We need to compute 3v. So it's just taking 3 times every entry of the vector v. Here, it is how to find it. 3v equal 3 times this vector we have given, which is 3 times every entry, as it has done here. Then 3 times 1, 3 times 2, 3 times 3, we get 3, 6, 9. The entries of the resultant vector, the vector obtained after multiplying the scar or the real number. Okay, dear students, this is another operation on vectors. It's called a dot product. Okay, let's talk more about this dot product. Dot product is multiplying two vectors and result to a scar or result to a real number. And here we are going to see just the vectors in 3 and 2 dimensions. Suppose you have u and v. These two vectors maybe are in either 2 or in 3-dimensional space. And they make an angle between them called angle theta. Now, the dot product is defined as u dot v. This u and v are dot products equal to the norm of vector u times the norm of vector v times the cosine of theta. Remember, theta is the angle between these two vectors. So, we have an example here. We need to compute the dot product between vectors u and vector v, which makes the angle between them 45 degrees. Okay, students, let's go to an example. Okay, dear students, let's see an example. We are asked to find the dot product between two vectors u and v, which makes the angle between them 45 degrees. Solution. So, from the definition of the dot product, vector u dot vector v equal to the norm of the vector u times the norm of the vector v. I mean vector v times cosine of theta. Okay, we know how to find the norm of the vector. Let's find the norm of the vector u, which is the square root of the sum of the squares of the entries of u. 0 squared plus 0 squared plus 3 squared. This is equal to 9, which is equal to 3. So the norm of u, vector u, is equal to 3. Let's see the norm of vector v. This equals 2 squared, the entries of the vector v. 0 squared plus 2 squared. This equals 4 plus 4, and the under root of 8, which is 2 under root of 2. And we have angle theta, which is 45 degrees. From the dot product of these two vectors, u and v, we are going to take the norm of u, which is 3, times the norm of v, which is 2 under root of 2, cosine, or simply call it cos of 45 degrees. So remember 45 is a special angle. So here it is 3 times 2 times under root of 2 times the cosine of 45, it is under root of 2 over 2. And here we are going to get 6. This cancel with this one. This time this is 2. 2 times 6, 3 gives 6. So therefore, the dot product of these two vectors u and v is equal to 6. Okay, let's go to the next. Okay, dear students, we have seen about the dot product of vectors. And these are different solutions or different examples, different solutions of different examples. I want to remind you one thing, that if you take the dot product of two vectors and it gives you 0, those two vectors are called orthogonal vectors. It means are two vectors which are perpendicular. They are making a 90 degree between them with the intercept. Okay, let's see what's the cross product of vectors. By definition, if you have two vectors, either in, just consider in 3-dimension space, then the cross product denoted by vector u with this sign of multiplication, vector v, and it's defined by this way. It's just like finding a determinant. Okay, students, let's see an example. We have given this one to compute the cross product of these two vectors u and v. Dear students, here we have given two vectors in 3 dimensions, vector u and vector v. We are required to find the cross product between the two vectors. From the definition, the cross product of two vectors v is defined by I, j, k, by these are unit vectors, starting with u, 4, -9, 1, 3, -2, 7. It's just like finding a determinant. Here is plus, negative, plus. So, you take I outside here. You hide this column and this row. You remain with finding a determinant of -9, -2, 1, 7. And then here, -j. This negative applies here. So again, you hide this row of this j, this row and this column. Remain 4, 1, 3, 7. And then k, you have this row, this column and this row. Remain with 4, 9, 3, -2. Okay. Here it's 9. What the determinant of this one? It's 9. Taking 7 times -9, which is -63, minus 2, -2 times 1, which will be 2, positive, minus j. 7 times 4 is 28. Then minus 3. See just the normal ways of finding the determinants. So -2 times 4, -8, minus 3 times 9, 27. And here, we get here is -61 I, minus 25 j, and this one is 35, -35. This and this are negative, so it's -35 k. And this is a vector I, j, k, represents those 3 different components of the vectors. So the dot product between vector u and vector v is equal to -60, 61 I, -25 j, -5 k. Simply can write negative 61, comma negative 25, comma negative 35. Dear students, let's see this theorem. This theorem states that suppose we have two vectors u and v, and all the two vectors are in three-dimensional space. Then the dot product between these two vectors is just the sum of the multiplication of the corresponding components of the two vectors. So instead of using the other definition I've already seen, that the dot product between two vectors in 3 dimensions equal to the norm of the multiplication of the norm of the two vectors times cos of theta. Theta represents the angle between them. Now we are going to see that these theorems can find the dot product without considering or taking the angle of the two vectors in consideration. Okay, let's go to prove this formula or this theorem. Let's go to prove this theorem. Okay, students, suppose we have two vectors. U with 3 entries means it is in 3 dimensions, and V with 3 entries means it is in 3 dimensions. Then the dot product between these two vectors is the sum of the product of the corresponding components of the two vectors. So let's prove this one. Okay, consider the following sketch or diagram. Let's say this vector u, the norm of the vector u, and this is the norm of the vector v. Remember, the resultant of these two vectors might be here, u and v. And these two vectors here makes here an angle theta. So from the cosine rule of trigonometric ratio, u, vector u minus vector v square equal to the norm of vector u square plus the norm of vector v square minus 2 norm of vector u times norm of vector v cos of theta, this angle. So, dear students, remember that this is the dot product of two vectors. So, it's the same as writing the norm u of vector u minus v, or you can say the distance between these, the square of the distance between the vectors, the square of the norm of vector v plus the square of the norm of vector v minus 2uv. So let's continue this side here. Taking this one in the other side, we get 2u dot v. These are two vectors. The dot of two vectors. And then take this one to the other side. We get the norm square plus the norm of v square minus the square of the difference or the distance between vector u and vector v. So remember, dear students, that the norm of vector is the sum of the square of its entries and the analog. So if you square it, you remain with u1 square plus u2 square. plus here is V1 square plus V2 square minus here we are going to have U1 minus U2 bracket square minus plus U2 minus here is U1 V1 U2 minus V2 square plus U3 minus V3 square. So if you continue here, you get U1 square plus U2 square plus V1 square plus V2 square minus, taking the square of this one, you will get U1 square plus V1 square minus, it means plus, if you take the square of this one, you get 2 U1 U1. Then plus, if you come to this one, remember this subtraction is working with all of this one. So it's minus U2 square minus V2 square plus 2 U2 U2. If you come to this one, you get minus U3 square plus, minus V3 square plus 2 U3 V3. Okay, if you continue here, remember this one is cancelling this one. This one minus this one over this one minus this one over. So you find all the squares are cancelled out. Remember that here we are working in 3 dimensions. So here there is also U3 square. Here there is also U3 square. And also here there are U2 square plus U3 square. And also here there is minus plus V3 square. So this one finish with this one. This one finish with this one. This one finish with this one. This one. So lastly we made with 2 U1 U1 plus 2 U2 V2 plus 2 V3 V3. And therefore you get 2 U dot vector V equals 2 out U1 U1 plus V2 V2 plus V3 V3. 2 and 2 will cancel. Then remain with the vector V, vector U dot vector V, which is U1 U1 plus U2 V2 plus U3 V3. And this is the end of the proof, which gives us what the theorem has told us. From the demonstration on how this proofs works, so you can see the real picture how these theorems, these proofs come to this one. Remembering these 2 vectors are in 3 dimensions. So now you can be given 2 vectors and you're asked to find the product between the vectors without being given an angle between them. This is just taking the summation for the product of the corresponding components of the 2 vectors. And now here you see how it comes very quickly. And now the product between these 2 vectors given there, it's C10, the dot product. Now you can be asking to find the angle between the vectors. Now, if you now know how to find the dot product without having an angle between the vectors, and we know how to find the norms. So you just find the angle is cosine inverse of the dot product of 2 vectors of the product of their norms. And now you can, from the given example, we get this one cos inverse. The product I was telling, the product of the norms of the vectors, this one. Now the angle is 70. So this is the, thank you so much, and this is the end of the first knowledge of linear algebra 1 or MT 112. Thank you so much.